All right, it's now time to move on to section 3.6. We are now going to be trying to do these things numerically. So, what does numerically mean? Numerically means pretty much we are going to try to take a really complicated math process and try to make it not so hard. And by hard, I basically just mean we are going to try to use processes we have been using forever instead of trying to use all of our new skills we have learned here so far in Cal 2. Let me show you what I mean. We actually did a little bit of this in Calculus 1. In Calculus 1, we did this really neat thing where if I was trying to find the area of a region, so like I'm just going to make it a basic graph like this, area of that, let's say I wanted to find the area inside of here, okay? What I did was I said, okay, let's do left endpoints. And I can find the area of this and then add it to the area. Sorry, I didn't draw that very well at all. Add it to the area of this one. Add it to the area of this one. Add it to the area of this one, right? We did that in Cal 1. What this is this is us numerically finding integral from a to b of f of x dx. How I would do this the proper way, we've done this a whole lot of times in here. You would take the antiderivative and then plug in the points, right? That is the calculus way. That is the new proper way. This was the numerical way because it used a process we already knew. We know how to do length times the width, right? We've done that a bunch of times, probably since you were in grade school, right? So this isn't hard. So what we did was we took a process that's not very hard and used it to do stuff that was kind of a little bit hard. That kind of makes sense. That's what I want to do here. So again, numerically is the quote unquote easy way without having to do all of this. Now, a big point I want to make though, although this isn't very hard, the solution I get is not exactly right, as I can tell here, because there's a whole gap right here. There's a whole gap right here. There's also extra pieces right here that I don't need, right? So this isn't exactly right, but for the most part, it gets us close enough to where I'm okay with it, right? So again, just want to make it clear, this is not exactly right, but it's going to get us close. This method is exactly right. So anyway, the numerical way isn't very hard, but it doesn't get us exactly right. Okay, so the first numerical method I am going to use is something called the trapezoidal rule. And it kind of builds off of what I just said over here that we did in Cal 1. So once again, if I was finding the area under a graph, I want to try to do a not so easy graph. Let's do this. And I want to find the area from here to here. Now again, the proper calculus way is that if this graph is f of x, this is a and this is b, you would do integral from a to b of f of x dx. That's the proper calculus way. I'm trying to do this numerically, meaning I don't want to do that. I want to find a way that's not very hard, right? So like I said before, in Cal 1, you would have done either left points or the right points and made rectangles, right? Just like we just did. Rectangles, just like that. With the trapezoidal rule, instead of doing rectangles, I want to make trapezoids. So let's say I have different points in here, separated evenly, like that. The trapezoidal rule means I'm going to go from my left point to my right point with a straight line. Straight line. And then make a trapezoid. Once again, straight line. go down, straight line, go down, straight line, go down, straight line, go down. Keep going the whole way. That's what I'm going to do for the trapezoidal rule. And then I'm going to find the area of each one of them. Area of this one plus the area of this one plus the area of this one plus the area of this one, area of this one, area of this one, area of this one, and add them up. That is the numerical way using the trapezoidal rule. What the trapezoidal rule is going to come down to, if I did that and you add them up, it's going to come down to this formula right here. Tn, that n is how many parts I'm going to do. So like for this one, I have 1, 2, 3, 4, 5, 6, 7. So that's my n, because that's how many parts I'm going to have. Okay. Tn is going to be 1/2 times delta x. Remember, that's going to be my change for x. Delta x is going to be the width of each part. That's going to be delta x. This is going to be delta x. I didn't draw this well, but every delta x should be the same. Delta x of f of my first point, so f of where I start, so in this case, A, plus 2 of f of my next point, plus 2f of my next point, plus 2f of my next point, on and on and on and on and on. And then my last one is going to be just 1f of my last point. Now, why do all of these have 2 except for my last one, except for my first one and my last one? Well, think about this. For this area right here, I'm using this line and this line. For this area right here, I'm using this line and this line. Well, you could have seen right there, this line is being used twice because I'm using it for this one on the left side and this one over here. Same thing with this line. This vertical line right here is being used twice too because it's being used here and it's being used here. All of the inside ones are being used twice. The outer ones are only being used once. So that's why they all have a 2 except for my first and my last one. So again, 1/2 times my change for x, f of my first point plus 2 of my next one, 2 of my next one, on and on and on, and then just 1 of my last point. So for example number 1, use the trapezoidal rule to estimate the integral from 0 to 1 of x squared dx using 4 parts. So just to draw what I mean, you don't have to actually draw these out. I'm just trying to show you what I want us to do. The graph of x squared is like this. And I drew that one because it was of x squared. So I'm drawing the x squared. I'm going from 0 to 1. Let's say 1's right here. And I want to split this up into four parts. So I'm going to try to do this trapezoid here, this trapezoid here, this trapezoid here, and this trapezoid there. That's what I want to do, which is going to turn into this formula I have there. So there are a few things I need. Okay. Again, I'm just trying to show what I want to do. You don't have to actually draw this out. You just have to use the formula. So for example number 1, first things first, I want to see what the range is, right? So I know my starting point is going to be 0, and I'm going to stop at 1. So I'm starting at 0, stopping at 1. And I'm splitting this into 4 parts. So how I find out how big each part is I'm going to divide this range by 4, again, because it's 4 parts. So the total length from 0 to 1 is 1. So my total length is 1, and I'm dividing it by 4 parts, again, because that's what they said, by 4. So each width is 1/4. So from 0 to my next point, I would have to add 1/4, which would put it at 1/4. Add another 1/4. 1/4 plus 1/4 is 2/4. 2/4 is 1/2. Add another 1/4 would give you 3/4. Add another 1/4 gives you the 1. So what this means when I plug it in, I want to find T4 because it's 4 parts. Starts with 1/2 out front times the delta x. My delta x is 1/4 because that's the width of each part. Times, and then plug it in here. So 1f of my first point plus 2f of my next point plus 2f of my next point plus 2f of my next point. And then the only point I have left is my last point, which I only do once. And now I've just got to work that out. 1/2 times 1/4 is 1/8. My f of x was x squared because that's the function I'm using. Again, how I know that is because it was of x squared inside of here, right? X squared. So f of 0 means I'm going to do 0 squared, which is 0, plus 2f of 1/4. 1/4 squared is 1/16, plus 2f of 1/2. 1/2 squared is 1/4, plus 2f of 3/4. 3/4 squared is 3 squared is 9. 4 squared is 16, so 9/16, plus f of 1. 1 squared is just 1. So now just simplify this down. So 1/8. 0 is just gone. 2 times 1/16 is 1/8. 2 times 1/4 is 1/2. 2 times 9/16 is 9/8 plus 1. The common denominator here is an 8, so then they all have to have 8. This one already has 8, so that's good. I need to times this by 4, so that's 4/8. This one already has 8, so we're good. I need to times this one by 8. 1 plus 4 is 5, plus 9 is 14, plus 4 is 22. 22 over 8, both of those have a factor of 2, so that can reduce to 11 over 4. And then 1/8 times 11/4 is 11 over 32. So what this means is that the integral from 0 to 1 of x squared dx is about 11 over 32. Once again, that's not exactly right, but it's using math that's not very hard to do something that's normally a little hard, right? Once again, as I will always say, if something about that doesn't make sense, please just let me know. No problem. I will be happy to help you out. Trapezoidal rule again with example number 2. Example number 2 says use the trapezoidal rule with n equals 2 to estimate from 1 to 2 of 1 over x dx. So again, we're using n equals 2 with the function 1 over x from 1 to 2. So once again, I have to figure out what the range and everything is. I'm starting at 1, I'm going to 2. So my total length from 1 to 2 is going to be 1, and I'm splitting it into 2 parts, so each width is 1/2. So to find my next point, I've got to do 1 plus 1/2. 1 plus 1/2 is like saying 2 over 2 plus 1 over 2, which is 3 over 2. And there are my 2 parts right there. So to do T2, remember there's always a 1/2 out front, times the delta x, which we said was 1/2 because that's how wide each part must be. Then times 1f at my first point, plus 2f of my next point. And then the only one left is my last point, so it's just 1f at that point. And then now simplify that out. 1/2 times 1/2 is 1/4. F of 1, f of x is 1 over x, not 1 over 2. What am I thinking? f of 1, so 1 over 1, which is just 1, plus 2 times. F of 3 over 2, 1 over 3 over 2, I can just flip it, and it's 2/3. Once again, 1 over 3 over 2, you just flip it and make it 2/3. Plus f of 2, plug in a 2, you get 1/2. So that'd be 1/4 times, this is still just 1, plus 2 times 2/3 is 4/3, plus 1/2. The common denominator there is going to be a 6. So that's 1/4, 6 over 6, plus 8 over 6, plus 3 over 6. 6 plus 8 is 14, plus 3 is 17. And 1/4 times 17/6 is 17 over 24. So the trapezoidal rule isn't that bad. I don't think it's that bad. Obviously, it would become harder if there were more parts. That's just more stuff you have to add up, right? But the process itself isn't too terrible. And the idea here is if I had infinite parts, so like if each width is really small, the smaller it is, the more parts I have, the closer I'm going to get to the actual right thing. But obviously here I only had 2 parts, so I'm not very close to the right one. All right, so that's the trapezoidal rule. The Simpson's rule is next. Simpson's rule is very neat. So think about what we have done so far. So in Calculus 1, our regions look like this, rectangles like this. With the trapezoidal rule, it looked like this. So this is just a horizontal line. This is a slanted line. What the Simpson's rule is going to do is instead have a parabola. So it's going to look something like this. The parabola is going to make us be even closer. Okay, that's what Simpson's rule is going to do. For those of y'all in my calculus class, and even those of y'all who aren't, the book we use is the OpenStax book, Calculus Volume 2. And in there's a really awesome proof of how they get here and what they are going to do with it. But basically, they just separate each part into something that's like this, do the areas, add them up, and you get Simpson's rule. S of n is going to be the delta x over 3. So up here I had over 2. Now it's over 3. F of my first point plus 4 f of my next point plus 2 f of my next point plus 4 f of my next point. And it'll just go on and on and on. 4, 2, 4, 2, 4, 2, 4, 2, up until my last point, which is just 1. So now we are going to use Simpson's rule. Simpson's rule is going to get us even closer. So example number 3, use S2 to approximate from 0 to 1 of x cubed dx. So n is going to be 2. The function is going to be x cubed, and we're going from 0 to 1. So once again, let's see what the range is. I'm starting at 0 and I'm going to 1, and I'm splitting it into 2 parts. So the total length from 0 to 1 is 1, separating it into 2 parts, so each width is 1/2. So to find my next point, do 0 plus the 1/2 gives you 1/2. So for S2, remember it's going to be the delta x divided by 3, or like how I have it written here, I could have written it as 1/3 times the delta x. So 1/3 times my delta x, which we said was 1/2, times f of my first point, and then always start at 4. Remember it goes 4, 2, 4, 2, 4, 2. Always start at 4. f of my next point, but then all I have left is my last point, so it's just one of those, and work it out. 1/3 times 1/2 is 1/6. F of 0, 0 cubed is 0, plus 4 times f of 1/2, 1/2 cubed is 1/8, plus f of 1, 1 cubed is 1. So that's going to be 1/6. 0's gone, right? 4 times 1/8 is 1/2, plus 1. 1/2 plus 1 is 3/2. 1/6 times 3/2 is 3/12, which is 1/4. So it's about 1/4. Remember, always go 4, 2, 4, 2, 4, 2, on and on. Sorry, that was example number 3 on the handout. So now let's move on to example number 4. Example number 4, again, use S2 to approximate from 1 to 2 of 1 over x dx. So n's going to be 2. The function is 1 over x. And the range is from 1 to 2. So same thing. Starting at 1, going to 2. My total width is 1, because from 1 to 2 is 1. And then I'm dividing it into 2 parts. 1 plus 1/2 is 3/2. So to do S2, it's going to be 1/3 times the delta x, which is 1/2, times the function, or times the function at my first point, plus 4 times the function at my next point. And then the only part I have left is my last point, so just one of those. 1/3 times 1/2 is 1/6. F of 1, 1 over 1 is 1, plus 4 times f of 3 over 2. 1 over 3 over 2 is 2 over 3, plus f of 2, which is 1/2. Let's keep working this out. 1 is just 1. 4 times 2/3 is 8/3, plus 1/2. Common denominator there is a 6. So that would give me 6 over 6. Need to times this by 2. 16 over 6. Need to times this by 3. 3 over 6. 6 plus 16 is 22. 22 plus 3 is 25. And 1/6 times 25/6 is 25 over 36. Once again, if that doesn't make sense, please let me know. No problem at all. Last example, example number 5. We are going to use S6 to approximate the length of the curve y equals 1/2 x squared. I'm realizing now I did not put the bounds. The bounds are supposed to be from x equals 1 to x equals 4. So we're going to do that from x equals 1 to x equals 4. Okay, so we learned length of a curve in chapter 2. As a refresher though, the formula for the length of a curve is the integral from a to b of the square root of 1 plus the derivative squared. So that's what I want to do here. So for this one, it told us that I want to, well, it didn't, but I did. I want you to go from 1 to 4. So we're going to go from 1 to 4 of the square root of 1 plus, I need to find what the derivative is. So the function was 1/2 x squared. So the derivative of that, using the power rule, right? I can bring 2 down. 2 times 1/2 is just 1. So that's 1x. So the derivative is x, so it's going to be x squared dx. So again, I want to use Simpson's rule, specifically S6 here. So again, break it up into a number line. I'm going from 1 to 4. I've got to find what my total length is. My total length from 1 to 4 is 3. Right? Because from 1 to 4 is 3 places. Separated into, they want it in 6 parts. separated into 6. So each part is going to be 1/2. So 1 plus 1/2 is 3/2. Plus 1/2 is 2. Plus another 1/2 is 5/2. Plus another 1/2 is 3. Plus another 1/2 is 7/2. Plus another 1/2 is 4. I didn't draw this to scale. Let's reduce it just so that it looks nicer. Let's put 4 there. There we go. That's going to be the range that I have. So for S6, 1/3 times the delta x, which we found to be 1/2, times the function at my first one is 1. Remember, I always start at 4 and then go 4, 2, 4, 2, 4, 2. 4 f of 3 over 2 plus 2 f of 2 plus 4 f of 5/2 plus 2 f of 3. Sorry, I'm just going to move this really quick. Plus 4 f of 7/2, and then my next point is my last point, so just 1 f of 4. Again, it just goes 4, 2, 4, 2, 4, 2, until my last point. 1/3 times 1/2 is 1/6. F of 1, so the function I'm going to use is this guy inside of here, square root of 1 plus the x squared. 1 squared is 1, 1 plus 1 is 2, so that's the square root of 2, plus 4 times f of 3 over 2. 3 over 2 squared. 3 squared is 9 over 2 squared, which is 4. So this is 9/4. 1 plus 9/4. This would be 4 over 4, right? 4 plus 9 is 13, so 13 over 4. But I'm taking the square root of it. So square root, square root. Square root of 13 we can't do, but the square root of 4 is 2. Square root of 13 over 2. Plus 2 times f of 2. 2 squared is 4. 4 plus 1 is 5, so that's the square root of 5. Then f of 5 over 2. 5 over 2 squared is 25 over 4. 1 plus 25 over 4. Once again, remember 1 is like saying 4 over 4. 4 plus 25 is 29. But I'm taking the square root of it. Square root of 29 we can't do, but the square root of 4 is 2. F of 3. 3 squared is 9 plus 1 is 10. So this is 2 times the square root of 10. F of 3, or that's a 7. 7 over 2 squared is 49 over 4. 1 plus 49 over 4. Once again, remember 1 is 4 over 4. 4 plus 49 is 53. Square root of 53 we can't do, so just leave it. But the square root of 4 is 2. Plus f of 4. 4 squared is 16, plus 1 is 17. So plus the square root of 17. Let's see what we can do here to kind of reduce this. Square root of 2, there's nothing I can do there. 4 divided by 2 is 2, so this is 2 square roots of 13. 2 square roots of 5, nothing I can do there. 4 over 2, again, is 2, so that's 2 square roots of 29. 2 times the square root of 10, nothing we can do there. 4 over 2, once again, is 2, so plus 2 square roots of 53. And then square root of 17, nothing we can do there. Now looking at this, all of these are irrational square roots, so there's nothing else I can really do. So y'all can just stop right there. Perfectly fine with that. All right, so once again, if any of this does not